Okay, today we're going to talk about ratios of areas. Okay, it's our topic. But today I'm going to kind of do it a little bit differently. I'm going to give you the end result. When you have the ratios of area, here's a theorem that talks about this. I'm kind of going to do it backwards. Okay, so let me give you the theorem that tells you something about the ratios of their areas. Okay, here we go. So let me give you the result. If the scale factor of two similar figure is a to b, this one you should know. Before we talk about the area, we're going to talk about their. Oops. Let me try to hide. Okay, whoops. Hide the answer. Okay, so before we talk about the areas, let's talk about the ratio of their perimeters. If the scale factor of two similar figure is a to b, think about like similar triangles or similar polygons. What do you think the ratio of their perimeter will be? We sort of did this when we were talking about these ratios of similar polygons, ratios of their corresponding size. What do you know about the corresponding size of similar figures? They are in proportion, correct? Right? So what do you think about their perimeter? Yeah, they'll also be in proportion too. Right? You're just basically adding up all these things that are in proportion, right? So guess what? If the scale factor of the two similar polygons is a to b, then the ratio of their perimeter is also a to b. But what about their areas? What do you think? Everybody go ahead and think about the ratios of the areas of the two similar figures. Go ahead. I'll give you time. Do you think it's going to be a to b? Okay, go ahead. What do you guys think about? All right. A lot of you have guessed it correctly. It turns out it's a squared to b squared. It will not be a to b. So we're going to actually think about why this is true. Okay. So this is a theorem. So the ratios of their perimeter is a to b, right? Just like their scale factor. It turns out the ratios of their area is going to be squares of their scale factor, a squared to b squared. Is that okay? And we're going to talk about why in a minute. And these are two similar figures. Very good. Keep that in mind. Do you think it will work for figures that are not similar? No. Okay, it only works. That's why it says similar figure. All right, keep that in mind as we do talk about this in a minute. Here we go. Knowing the theorem, let's do some examples here. It says find the ratios of the areas of two triangles. First triangle we want to talk about is the triangle with equal heights. Are they going to have the same base then? Also? No. Okay, they just have equal heights. So here's and then second one, what about the ratios of the areas of two triangles that have equal bases? Thirdly, two triangles that are similar. Well, actually, we know the result for this one, right? What do you know about the ratios of the area of two similar triangles? They are a squared to b squared, not a to b. If the two triangles are similar, these are similar polygons, right? If two triangles are similar, we know that the ratios of their area is a squared to b squared, right? So we know the result for the third one. Let's talk about this in a minute. So let's look at the first one. Do you think with the equal heights, it's going to be a squared to b squared also? We'll see. Okay, let's take a look at it. Let me actually draw a triangle that happens to have the equal height, but have a different base. Is that okay? So here is how I could. Here, take a look at this. Here we go. So take a look at this picture. Here, I have drawn a triangle that happens to have the same height, different base. What is the height of both of these triangles? Green one and the orange one. H, right? By the way, is this the height of the? Is the H height of this orange one really? Yes, it is. Is it okay? Is it possible for the height to be outside the triangle? Yeah, because look at this vertex. Remember, we defined height, right? From the vertex, is this perpendicular line to the base. Well, if there's no base, you have to extend the base, right? You guys remember that? So both of these have the same height. They have different base. One of them has a base of A, the other has a base of B, right? So let's compare the areas of the two triangles. Somebody tell me the area of the green triangle. How about? Okay, how about call somebody at random here? Let's see. How about Hannah? Can you tell me the area of the green triangle? Yeah, half of AH. Very simple. Well, somebody give me the area of the orange triangle. Krista? Half times pH. So, well, to figure out their ratio, it's easy. Just write it down like this. Okay. So, right, the area of the ABC, the green one over the orange one, is half AH over half pH. Now, is that the simplest way to write this? No. How do we simplify this further? What does it give you when you simplify? Shanna? AH over pH, but they both have H on the top and bottom, so could we cancel it? So it just simply becomes A over B, right? So it turns out if the two triangles have same height, okay, and they have different base, the ratio of the two triangles is the ratio of their bases, right? Shouldn't we have gotten A squared over B squared? Why not? Didn't we say if the two triangles are similar, the ratios of their areas was A squared over B squared? How come we didn't get A squared over B squared? Okay. Michelle? Yeah, these two are not similar triangles. By no means, right? They both have the same height. Okay. So these are not two similar triangles. It only works for similar triangles. That's why we... Alright, is that okay? Do you get the idea? So it turns out if the two triangles have the same height, okay, and different base, you just have, if you wanted the ratios of their area, like a lot of things cancel out the heights in half, right? So it's going to be simply the ratio of their bases. Is that okay? All right, so keep that in mind when you do your homework tonight. It may be helpful. All right, let's look at the second one. What do we say? We're going to then, instead of having the same height now, let's think about a triangle that has the same base. Here is a triangle. There we go. See? Kind of, the way they drew it is kind of clever because they share the same base, right? Does it have to look like this? Could it be separated? Yeah, it's fine, right? But as long as they have the same base, it doesn't matter. They have different height. One of them has a height of H, the other has height of K, correct? So somebody tell me the area of, let's look at the triangle ABC, the bigger one here. How about Brandon? Here, what do you think? What is the area of this triangle ABC? 1/2 pH, right? Very good. Somebody tell me the area of the other one, the smaller one, ADC. Emily, what's the area of the other one? 1/2 kb. So, of course, we could just write this out. It's pretty simple. And now, of course, that's not the simplest way to write, right? When you simplify this, what do you get? Leo? H over K. The B's cancel out, the half cancel out, right? You get simply H over K, correct? So what have you found? Well, the ratios of their area is simply ratios of their heights. Does that make sense? Kind of similar as A. Again, are these two triangles similar? No, that's why it didn't come out to A squared to B squared. Well, now the C is where the two of them are similar, right? So let's take a look at C. Are people still writing down? Oh wait. Okay, go ahead. All right, now let's take a look at two similar triangles. Okay, the two triangles ABC is similar to triangle DEF. Now, what do you know about similar triangles? What do you know about their corresponding sides? They are in proportion. And I don't know if you remember this. You actually did this as your homework or something like that. What do you think? I'm just going to tell you. What about not only the corresponding size, but what about the corresponding heights of the similar triangles? Do you think they would also be in proportion? Yes, they will be. Okay. So look at H and K. Right? These are not size of the similar triangles, but it turns out they're in proportion. Does that make sense? Are you all okay with that? Okay, so it turns out the heights are in proportion. So let's then figure out the ratios of the areas of these two similar. We know it should come out to A squared to B squared. Well, I don't have any A and B, but you know, whatever the scale factor is, it's got to be square of those, right? Does that make sense? So somebody tell me the area of the triangle ABC there. Jordan, what is the area of the triangle ABC? 1/2. 1/2 times BH. Exactly right. What about the other triangle? Joshua? Over here, yeah. 1/2 times EK is correct. So let's write it down. So let's compare these two areas. And I get half cancels out. I get B over E times H over K. Right? Unlike last time, things don't cancel out. This doesn't look like squares of its rate, squares of scale factor, does it? I got B over E times H over K. What's going on? I thought we're supposed to get squares of their scale factor.
It's not simplified.
Well, how do you simplify this more? Okay, turns out it'll be squares of their scale factor. There's a way to do it. Okay, go ahead, everybody. Then think about how you could do this. Okay, go ahead. Go ahead. Think about with the group. What do you think? How does this turn to squares of their scale factor? Go ahead, everybody. Think about it. Okay, how many people realize that? Wait a minute. We know that the two triangles are similar, and what do we know about corresponding size of the similar triangles? They're in proportion, and we also said that the heights are also in proportion, right? Okay. So, Kenneth?
Yes.
Can you tell me what ratio is B to E equal to?
B to E.
Uh-huh.
H to K.
H to K is correct. So then, how does it help us to see that the ratios of the areas of similar triangle become squares of its scale factor? We know that H to K must be equal to B to E, right? So what do we do next? How about Grace? Okay, I'll give you more time, guys. Go ahead, everybody, think about this. How does this work out? How does it become squares of their scale factor? This is a big hint, right? So, Grace, what did your group come up with? Yes.
Substitute it into that top equation with B over E.
That's right. Look, we said B over E. When we looked at the areas of the two triangles, similar triangles, we get B over E times H over K, right? Well, what is H over K? B over E, and when you plug it in, what do you get? B over E squared, right? Squares of their scale factor. Does that make sense? Okay, so that's sort of a proof, right, for that theorem. If you have two similar triangles or two similar, not as a matter of fact, for polygons, right? If you look at the ratios of their area, it's going to be scale factor squared. Squares of their scale factor, right? A squared over B squared. If the scale factor is A to B. Does that make sense? Yes? Okay, so knowing this, let's do some examples, okay? By the way, here's a little bit of a summary. You don't have to write this down, but let me see whether you could figure this out on your own. If two triangles have equal heights and their ratio of their area equals to what? To the ratio of their bases. Very good. What if the two triangles have the equal bases? Then the ratio of their area equals to the?
Equal heights.
Very good. Ratio of their heights. Thirdly, Reagan, what do you know about if two triangles are similar? Then the ratio of their area is equal to the squares of their? Which is called the scale factor, right? Scale factor. The corresponding parts of that triangle. That gives you the scale factor. Does that make sense? So this is what we just talked about in terms of those three examples, okay? All right. Here's example 2. It says if you have a trapezoid ABCD, and it says find the ratios of the areas of triangle COD. Where's that one? Oh, it's the yellow one. COD and AOB, the one on the bottom right here, right? They want you to find the ratios of their area. Also, COD again and AOD right here. This one, the one triangle. Okay. Lastly, triangle where is it? Oh, OAB. OAB, this one right here, OAB to DAB, this whole thing. Okay? So go ahead, everybody try this. Now, the exercise that we just did will be helpful. But go ahead, everybody try. I'll wait for it. Everybody try as a team. So, first of all, let's just look at A. Okay? You know what they did for you? They actually drew this nicely for you. Not A. Oops, that's B, sorry. A, they haven't, sorry. But you can see, what do you know about the two triangles for A? COD, the yellow triangle, versus the one right underneath. By the way, how come they put tick marks here and here? Because they haven't said anything about those angles being congruent. How do they know that they're congruent? How about, David? How do you know that DCO is congruent to OAB? Good. Therefore,
Alternating.
yeah, these are alternating interior angles of two parallel lines cut by a transversal. And with the same reason, you could say angle CDO is congruent to OBA, right? Does that make sense? So the two triangles are similar by angle. Or you could say, you know, the vertical angles are congruent, whichever way you want, right? So we know that for sure the two triangles are similar. Is that okay? Well, we know something about similar triangles, don't we? What do we know about the ratios of their area? It is going to be what? How about Youngwoo? So we know, we just said that the two triangles are similar, right? So we know then the area, the ratios of their area of similar triangles. What would it be? What is, by the way, what is the scale factor of these two triangles? Mm-hmm. It's going to be 3 to? Yeah, so therefore, if you're looking at their area, the ratios of their area, what it would be? No, it's not 3 to 5. We just learned this. What do you know about the ratios of the area of the ratios of similar triangles? They are scale factor what, Youngwoo? The theorem that we just talked about. Scale factor. What do we do with the scale factor? It's not scale factor. Yeah, it's a squared to b squared. A to b is their perimeter, not the area, right? Okay, so it's a squared to b squared, therefore it comes out to, how many people got 9 to 25? That's the answer. Very good. Very good. Okay, very good. So the A was pretty straightforward. Now, knowing A, we could do B. Because, by the way, 9 to 25, is that the ratios of their corresponding size, or is that the ratio of their areas? Area. So what do you know about the corresponding size? For example, because I'm not, look at B. COD, the yellow one, versus AOD, which is the one right next to it. What do you know about CO versus OA? CO and OA. Yeah, the ratio's got to be 3 to 5 because look, if you look at the triangle on the top and the triangle on the bottom, right, aren't these corresponding parts of these two triangles, one on the top and the one on the bottom? So it's got to be this. It's got to be 3x to 5x. How come they wrote 3x to 5x, not 3 to 5? Hold on. Why is it 3x to 5x, not 3 to 5? Jonathan? Okay. Let me give you a hint. If I say 3 to 5, does that, it means this length has to be 3 units, this has to be 5 units. Is that necessarily true? Yeah, it's just their ratio is 3 to 5, right? So to represent that the ratio is 3 to 5, we don't know exactly what they are, but we know that the ratio has to remain 3 to 5 because that is a corresponding parts of this triangle, and then this is corresponding part of the one on the bottom, right? So those are 3 to 5, so it's got to be 3x to 5x. Is that okay? Now, some of you might think it's 9x to 25x. Would that be correct? Why would that not be correct? Didn't we just find 9 to 25? What is 9 to 25, that ratio? What does that represent? That represents the, Katie, areas, the ratios of their areas, not ratios of their corresponding size, right? So please be careful. On the homework or test, people get that mixed up, okay? 9 to 25, that's the ratios of their area. Here, we're just looking at the ratios of their corresponding side, which is 3 to 5. Is that okay? Knowing this, some of you said this, what can you tell me about these two triangles? Hint, hint, look at the H. What is sort of interesting about these two triangles? Jack? They both have same what?
They have the same height.
They both have same height, don't they? And what do we know about two triangles that have the same height? When you're looking at the ratios of their area with the same height, we just learned that their ratio is what? The ratio of the bases. So it comes out to what? Nico? The ratio of these two triangles, the areas of the ratio of this triangle that has the same height will be what? We just said that if the two triangles have the same height, the ratios of their area is going to be ratios of their what? Bases. And look at the bases of these two triangles. What is the ratio of these two bases? Which is 3 to 5. So this comes out to 3 to 5. Any question? Does that make sense, guys? And if you wanted to, you could actually compute the areas, right? Which will be what? Half of 5xh, and then you get half of 3xh, right? And then you could cancel things out. But didn't we already figure that out? It's simply the areas of the ratios of the areas of the two triangles with the same height will be the ratios of their bases. Right? Does that make sense? Any question there? Are we good there? All right, then let's look at the last one. CAB, which is, OAB, which is right down here, OAB versus DAB, which is the whole thing on the left, right? What do you know about, what can you tell me about those two triangles? OAB and then the DAB. Who sees something interesting? One person see it? 2, 3? Okay, go ahead and talk about this with your team. What do you guys know something that's interesting about these two triangles? OAB and then DAB. What do you guys see? Okay, a lot of you already figured out. Okay, here's a picture. They actually drew it for you separately. What do you notice about the two triangles? How about, what did your group come up with? Joshua over here? Okay, Joshua, let me give you a hint. Look at this. Look at these two triangles, right? We're looking at this triangle OAB. You know the light blue one? And then this whole thing, DAB. They both share the same base. All right, look. The base of this light blue triangle, OAB, is AB. The base of this whole thing, right, DAB, the whole thing is also AB, right? So what do we say about two triangles that have the same base? If we were to look at the ratios of their area, it's going to be the ratios of their height. So all we have to figure out then is the ratios of their height. Then we'll be done, correct? So how do we figure out the ratios of their heights? Okay, you understand what we're trying to say? Because if you know the ratios of their height, we're done. Right? Go ahead, everybody discuss it with your group. Go ahead, what do you guys think? How are we going to figure this out? So, what did you guys think about this? So, by the way, here, they actually drew this. That's a sort of a nice hint? What do you think they did that? We still have that triangle on top and then the triangle on the bottom. What do we say about triangle DCO and then ABO? What do you know about those two triangles? They were similar, weren't they? So what do you know about their heights? They're in also proportion, right? We know that the sides are in proportion, their heights are also in proportion. So you see these two heights are 3y to 5y. Would you not agree, the ratio? So then, how does it help us to figure out the ratios of the two triangles OAB to DAB? Because they have the same base, all we need to know is the ratios of their heights. So, okay. Go ahead, guys, finish it up with your group. What do you guys think? Does that make sense? So knowing this, guys, what is the height of this triangle on the bottom, AOB? 5y. What is the height of this whole thing, DAB? 8y, because this is 3y over here, this is 5y, right? Aren't they parallel, the trapezoid? So isn't this the whole thing, the height of this whole triangle, the big one, DAB? So therefore, we know they have the same base. If the two triangles have the same base, we know then the ratios of their area, right? With the triangle that have same base, it's going to be the ratios of their height. So what's the answer? 5 to 8 is correct. Does this make sense? Right? It's 5 to the whole height, 8, right? 5y to 8y. Therefore, the ratio has to be 5 to 8. Does that make sense? Any question? Okay, help your teammates, see if they got this. So going back to the theorem that we started with, we know that if the scale factors of two similar figures, not necessarily triangles, right? Two similar figures A to B, we know that then the ratios of their perimeter is A to B, and the ratios of the area is A squared to B squared. So what if I know, here's a picture. Here's a problem. What if we say that the ratio of the two perimeter of the two similar figure is 8 to 12? Okay. This says find the ratio. Okay, so if the two similar figure, if the ratios of their areas, okay, let's read it, sorry. So find the ratio of the perimeter and the ratio of the area of the two similar figures. Look, what is their scale factor? A to? 4 to 3. Yeah, 4 to 3. Yeah, 3 to 4. Right? Does that make sense? So what is going to be then the ratio of the perimeter, class? Yeah, 8 to 12, which is 2 to 3. Yeah? Okay, hold on. What about their area? 4 to 9. Does this make sense? Does this make sense? Have a great day, guys.